Hello, today we're going to be looking at this problem where we are trying to maximize our total profit. First off, I wrote down some letters that I'll use throughout my explanation, where P is profit, R is revenue, C is cost, and then Q is quantity, and little p is price. We are also given our equation P1 equals 600 minus 0.3 Q1, and P2 equals 500 minus 0.2 Q2. And then we're also given total cost equals 16 plus 1.2 Q1 plus 1.5 Q2 plus 0.2 Q1 Q2. All right, so we want to determine how much of each product should be produced and find the maximum profit. So each product is going to be given to us by these Q1 and Q2 because those are our quantities of product. So we're going to be looking for a Q1, Q2 value coordinate, where then we, on our z-axis, once we take it three-dimensionally, that z value is going to be our profit. So the first thing that we have to do is we have to find the critical points of a function. And these numbered instructions throughout the video are going to be instructions just straight from my lecture notes of how to maximize a function in like this. So the first thing that we need to do is find the critical points of f in the region R. That's just general. Obviously, we have letters different than F and R. So the first thing that we have to do is create our equation. Revenue is given by the price of the first product times the amount of times you sell it, and the price of the second product times the amount of time that you sell that. But that is not enough for us. We need how much we gross. But our revenue itself is going to be open parentheses 600 minus 0.3 Q1 times Q1, or excuse me, 0.3 Q1 close parentheses Q1 plus open parentheses 500 minus 0.2 Q2 close parentheses Q2. So our profit is going to be revenue minus cost. It's what we bring in versus what it took to make that, to make what you were selling. So now our full function is incredibly disgusting to look at. I apologize for the biased language, but unfortunately I will not be reading this for you today. So now that we have our equation and we have profit in terms of Q1 and Q2, that's exactly what we want, because we are looking for how much of each product should be produced and the maximum profit. So this is a function of profit based off of quantities of items, so that is a really good sign, and it proves that your work, or the work that we've done so far, is accurate and good. Yay! So now we're going to find the critical points. We start by taking the derivative of P with respect to Q1 and Q2. P with respect to Q1 is going to be 598, and then negative, you bring down this 2, and then you get negative 0.6 Q1. This becomes 0 because when we integrate, when we derive, anything that does not have what we're looking for is viewed as a constant. So this Q2 means nothing, and the derivative of a constant is always 0. So this becomes irrelevant, and then this is more Q2, no Q1 at all, so that's also irrelevant. This 16 is a constant, becomes 0, and then we have 0.2 Q1 and Q2. The derivative Q1 is going to be 1, and then we are left with minus 0.2 Q2. And using the same logic, we get P, partial of P with respect to Q2 equals 498.5 minus 0.4 Q2 minus 0.2 Q1. So using those same values, I am going to find the critical points. So that is, these critical points are going to occur where the derivative equals 0. So we're just going to go through and check where each of these derivatives equals 0. So the first thing I notice is that I can take this q2 and I can set it off by itself. And then our move from there is going to be to plug that in to our other partial derivative, because we've set these both equal to 0, so we can treat these like a system of equations. So then after that, we do algebra, and we get q1 equals 699.1 and q2 equals 896.7. And so these are the values of our critical point, and we have our first critical point. So now our job is to classify it. For this, we need to look at D, which is given to you in a textbook. It is the partial of, well, it requires second derivatives. So first, we need to go through and find second derivatives of P with respect to Q1, Q1, P with respect to Q2, Q2, and P with respect to Q1, Q2. Whew, that's a mouthful. All right, so thankfully, these are pretty simple from here, just because none of these are raised to any powers. So all of these are just numbers. Now, so we have these. With D, it calls for the partial derivative at a point that we're looking at. In this case, it would be 699.1, comma 896.7, but since they are the same value wherever they are, we just plug them in. So partial with respect to one variable times, or second partial derivative with respect to one variable times the second partial derivative with respect to the other variable, and then you subtract the partial derivative that is both of them. So in the example that it gives, it's partial of x, y. And so then from there, we just need to find whether D is equal to, less than, or greater than 0. And in this case, it is positive, so it's greater than 0. So then I plugged that into my function in my graphing calculator, just because I believe that quantity of algebra would drive me insane. So now our point was found to be 7.21 times 10 to the 10th. And this is very, very much greater than 0. So since these both are greater than 0, it tells us that there is a maximum at this critical point. And now it seems like we should be done, but we have a boundary. And not all functions have boundaries, but since this is and has a real world application, we need to know that neither price nor quantity will be negative. So P1, P2, Q1, and Q2 must be greater than or equal to 0. So we'll just go ahead and look at these, because these are the things that we're changing around in our function. And so we'll check one of them at a time, with the other being 0. So for Q1 equals 0, and then we do this, and notice it looks very similar to our partial derivatives, just because we're isolating variables, which seems pretty cool to me. And all right, so we get our partial, which is almost exactly the same, except there's no x, y value, so to say. So we just set that equal to 0, and we get Q2 equals 1246.25. So we know that there is a critical point at 0, 1246.25. And then, so we just do the same thing with the other one, and for Q1, we get 998. So we know that there is a critical point at 998, 0. All right, and then, so from here, it is just looking at our values. So I also did the math for these in a graphing calculator off camera. So the value for P of 0, 1246.25 is 3.11 times 10 to the 5th, and for P of 988, comma 0, it is 2.99 times 10 to the 5th. So those values are very close, but if you'll recall, our other value and these numbers that I've been discussing are, once you plug them back into our function of p, our original one that we had back here, this function. So once you plug it into that, that is how you get these numbers, and that is giving us the total profit. And that's what we're looking at. We want to know the total profit. So for this one, the profit is 10 to the 5th, 10 to the 5th, and this one is 10 to the 10th, which takes the cake by a lot. So at 699.1 products at 699.1 of product 1 and 896.7 of product 2, you can make $72 billion. Wow. Easier calculated than done, I assume. All right, that's all that I have for you today.